G'day, my name is Brendan. I'm here to talk about a widely used performance metric called load averages, and I'll be talking about how they work on Solaris-based operating systems, including Solaris 10, Joint's SmartOS, Illumos, and others. Load averages are used to get an idea of CPU usage, and it's printed out by various tools, including PRStat, Uptime, W, and Top. It prints out the 1 minute, 5 minute, and 15 minute load averages. What I'd like to do is I'd like to give you a quick rundown on how they work, and then I'll go through and give you a more detailed description of the load averages, and I'll include some surprising details. So, to describe how this works quickly, consider a single CPU box. As you apply load to a single CPU box, that single CPU will have utilization that goes from 0 to 100%. The load average, and I've drawn a graph here with load average on the x-axis and CPU utilization on the y-axis. The load average for that single CPU box will go from 0 to 1 as work is applied. Once you get to 100% CPU utilization, it can't process any more code at the same time. So what will happen is, as software processors or threads want to use CPUs, the CPU, they will queue. And what that is it's a measure of saturation, applying work that resource can't dispatch. As more software threads queue, waiting for the CPU, the load average increases. And the distance above 1 gives you an idea of, on average, how many threads are waiting on the queues, waiting for their turn on CPU. So, for a single CPU system, you can come up with some very quick and simple rules. If the load average is less than 1, it means that there's probably idle, that there should be idle time on the CPU, and you haven't run the system at saturation yet. If the load average is over 1, it means you do have saturation, and it means some threads will be waiting their turn on CPU. This becomes a little more complicated for a multiple CPU system. So here I've drawn up a 2 CPU system that's running with a load average of 5.0. So I've drawn a thread as a dot. Each CPU has 1 thread running on it, and there are 3 threads that are queued up. So if that was steady state over time, the load average here is 5.0, which tells us there is 1 thread always on the CPUs, and on average there are 3 threads that are queued. It's harder to come up with such simple rules like it was for a single CPU box, but something that kind of works is to divide the load average by the CPU count. So if I take 5.0 and divide it by the CPU count, which is 2, I get 2.5. That's over 1.0, which tells me that the system's always running at a level of saturation. Now, to explain this, what I'll do is I'll add a couple more CPUs so that we can see what happens, while keeping the load average 5. So, if this was a 4 CPU box and the load average was 5.0, then what you would have is 1 thread on average always on the CPUs, and only 1 thread queued up. This is different. If I divide the load average by the CPU count, which is 4, then I guess a scaled version of the load average would only be 1.25, which indicates a lower level of load than the 2 CPU example. Even though numerically the load average is 5 on that 2 CPU box, and the load average is 5 on the 4 CPU box, the 4 CPU box is running at a lower level of saturation. If you'd like to think about this, if you'd like a way to think about this, imagine, and sorry for the analogy, but imagine these are toll booths at Golden Gate Bridge here in San Francisco, and you're driving up to cross the bridge, and the threads are cars. If I was to drive up to the system here, then I would not get into this lane, but I'd get into one of these other lanes so that I could get onto the CPU sooner. With the 2 CPU diagram, which I've rubbed off, but this is how it looks. Even though the load average is the same, if I drive up to the toll booths, I am definitely waiting behind a thread before I get to pay my toll and cross a bridge. So even though the load average is the same, the number of CPUs does matter, as that will affect how long I'm waiting on that queue. So that's a very quick way of understanding load averages. They're a measure of CPU usage, and tools such as PRStat and Uptime print out 3 values, the 1, 5, and 15-minute load averages, which by comparing the values, you can find out if the system is getting busier over time, or if it is staying the same, or if it is getting less busy. So at the moment, so here I can see 6.29, 6.45, and 6.73. This system is becoming less busy because the 1-minute load average is lower than the 15-minute load average. Now what I'd like to do is talk about how these really work. You might notice in the video about now, we're only about a third of the way in, so there's quite a lot more material to cover, and this includes some surprising details. If you think about load averages the way I just described, you do have a working knowledge of load averages, and in terms of how utilization and saturation are conveyed by that single value. So you don't really need to watch the rest of this video, but if you'd like a deeper understanding of how they work, please do. So how load averages really work is they're based on microstate accounting, which is a feature added to recent Solaris versions of the Solaris operating system. And I've drawn a diagram here that shows how it's calculated. And it does get a little bit complicated, but please bear with me. The clock routine is the standard timer on Unix that runs 100 times a second or 1,000 times a second, depending on your tuning. It has a variable 1 sec. Once a second, it runs various routines to update the system's load averages. So the first thing it does is it runs load average update, which goes through the list of CPUs and then adds together the CPU user time, CPU system time, and a variable CPU wait RQ. And because I'd like to talk about this in details, just to see what that looks like, here I'm in clock.c. And this is the load average update function. And it's calculating CPU total as this is CPU microstate accounting, and it's adding up the user microstate, the system microstate, and CPU wait RQ. These microstates, what they actually are is each time threads change context on the operating system, it records high-resolution timestamps of how long the thread spent in that particular state. So, to be clear, we aren't sampling what's happening on the system at a particular rate, say at 100 hertz or 1,000 hertz. What it's doing is it's taking the delta time based on these high-resolution timestamps and adding them to high-resolution counters. So it is a very, very accurate way to track how much time you've spent in various states, and it's not susceptible to sampling errors. These are the CPU microstate accounting members, and this one, CPU wait RQ, is the thread. This is incremented when we do restore mstate. It goes and adds the thread's wait time. Now, thread wait time is when you enter a dispatcher queue, as part of the thread structure, it will save a high-resolution timestamp. And when you take it off the dispatcher queue to be executed, it can calculate the wait time for that thread, and then it will add it to the per CPU structures. So that seems kind of strange, but the net result of this is the load average value still resembles this model that I talked about, which by now you've realized is not really true. It resembles this model, but it does so very, very accurately. It's definitely not sampling the length of these queues. What it's doing is it is adding up the time spent waiting from all the threads on the dispatcher queues, plus the user time and system time from each CPU, and deriving the load average based on that. The time spent on the queue, you may actually have some familiarity with it, if you use PRstat minus ML for microstate accounting, that is the LAT column, which is the, here I've run PRstat minus ML for microstates and L for the LWPs, light-weight processes, which are threads. And LAT is the percent of time that thread spent waiting on the CPU dispatcher queues. So this is the value that's actually added up. It does get added to the CPU structures. It gets added up and turned into the load average. How that works in a little bit more detail, we take these values and they're populated into an array of 10 members, which is part of the CPU structure, CPU-T. This is CPU load average, LG loads. And this steps through the 10 members. Each second it will step to the next member. So, and it will rotate through this array of 10, so that it has the last 10 seconds worth of load average. That, and apart from doing this per CPU, this is also done system-wide. So it actually adds up all of the load averages derived on these high-resolution metrics. This is added into a system-wide variable called load average. Again, it has the previous 10 seconds, and also adds it together per CPU partition. That's if you're using processor sets or using pools. It does record the load averages for each of them as well. That information is then fetched by generate load average, which takes the average of the previous 10 seconds and then feeds it into a routine called calculate load average that then gives us the numbers that we see. This averaging, you can think about this as a first pass at dampening the load averages. These do fluctuate quite a fair bit. Threads, you might have an event that wakes up a lot of threads and they enter the ready to run state and are dispatched, and you have a period of idle. By taking the average of the previous 10 seconds, and that's why it needs to have an array of 10, it needs to record each of these values. By taking the average, it does a first pass at dampening this value. Then it's added, it's fed into calculate load average, which generates the 1, 5, and 15 minute averages. Just a few notes before I get into that function. I said this is done per CPU. It's done system-wide in a variable called load average, and it's also done per CPU partition. So in the man pages for some of these tools, it will say that if you are running the tools on a system that's using pools and using processor sets, the performance metrics you're looking at are relative to that particular pool. And this is a mechanism of resource controls. And that is true for the load averages. If you've configured a system where you have processor sets and pools, you may put a zone on top of that. Then when you run uptime, or you're running whatever and you're looking at the load averages, it's relative to the particular processor set or pool that you're in. For Solaris zones, I don't see that set up too often. That's not how we set things up currently for Giant SmartOS. So when you run the load averages, these are actually system-wide, which can make them a little bit confusing because they may vary from second to second. That's something that we may update. So it does have the per CPU partition has been done, and that does get consumed. If you call uptime, it will go and read the appropriate location of the load averages. One thing that's never been done is the system is tracking load averages on a per CPU basis. So the rest of the infrastructure isn't really there from user land, but you could write a tool to actually print out per CPU load averages if that made sense at all on a system. That could be a dtrace-based tool. You can imagine we may want to add extra infrastructure here so that we can track this per smart machine. So the calculate load average, so given this information, and now I'm particularly interested in the system-wide load average, which is fed into calculate load average, that generates the 1, 5, and 15 minute values. And I've got the function here. This is calculate load average. And the color of the comment might be a little dim, but it's saying to compute the load average of the last 1, 5, and 15 minutes, it's calculating this based on an exponential decay, and it has some hardwired values which it feeds into this algorithm. As a software engineer, each time I see hardwired values inside code, my teeth clench, because sometimes that can lead to code that's a little tricky to maintain. You like to see constants, things to have names. This shouldn't be too bad in that these aren't likely to change anytime soon. That's part of how exponential decays work. What this actually means is, to start with, the 1, 5, and 15-minute load averages, that's not the average for 1 minute, and that's not the average for 5 minutes, and that's not the average for 15 minutes. This is actually an exponential decay. So the first pass took those 10 seconds worth of values to dampen the load average metrics, and then the second pass will decay it. So you'll see load average can, if I was to suddenly execute a whole bunch of new work, load average would change quickly to start with and then flatten out like you'd expect for an exponential decay function. And let me draw that graph a little bit. So let's say I run 5 threads on an idle system. I'd expect my load average to get to 5.0. So here's my load average. What actually happens is I have an exponential decay. So it will move quickly to start with and then take a while to get there. Given an exponential decay, how can we say 1, 5, and 15-minute load averages? So at which point on the curve are we at 1 minute or 5 minutes or 15 minutes? How quickly do these actually change? And to try and understand this better, I actually took this code and executed it in isolation as part of a C program, and then performed my own experiment to confirm my suspicions. What I did was I took an idle system and I ran one thread that was hot on CPU. What I would expect is over time, the load average would get to about 1.0. As it turns out, there's a baseline of load on this system, about 0.05. So I'm only running one thread. So this system should get to 1.05. That's how it looked at 1 minute. The 1 minute load average is actually only 0.66. At 5 minutes, the 1 minute load average has reached the target that I'd expect. This time the 5 minute load average is only at 0.68. And at 15 minutes, the 15-minute load average is about 0.68. This is, you can see a pattern here, and that is, if you subtract the baseline, and I confirmed this anyway by running the code manually, the point for the 1, 5, and 15-minute load averages, the target point, let's say I was to write 1 minute here, is about 63% of where it should be. So if you're looking at the 1 minute load average, it's not an average, an equally weighted average over the previous 1 minute. It's taken the previous 1 minute of data and that's contributed 63% of that value. And there's still past time that's contributing to that load average. And it's the same for the 1, 5, and 15-minute load averages. So these things are quite tricky to understand. They're not as simple as they would seem. They do eventually settle out, as you can see at the 5 minute mark when my 1 minute load average did settle. Even at 15 minutes, obviously my 15-minute load average still has some time. You can, if you'd like to understand this in even more detail, you can read the source code yourself. It starts from clock.c, and as I described, a very simple way of thinking about it is to add the utilization of the CPUs and the number of threads that are queued. How it actually works is the microstates for CPU user and system time plus the length of the the CPU latency from microstate accounting. It's dampened once, just to, I guess, remove the fluctuation, and then we have these exponential decays, so that it will reach its the 1, 5, and 15 minute averages at about that's about 63% of the value. And just to stress one last time, the load averages for joint smart machines and for Solaris 10 zones, currently the load average is, if I run and I'm logged into a joint smart machine here, if I inspect my load average, it says 6.79, which may tell me that there are over 6 threads that would like to run on CPU. I need more than 6 CPUs for them to actually get their turn. This may not be my smart machine. This may be other people in the system as well. If you'd like to understand your load average, your CPU usage, you can use PRstat minus capital Z. And so on my smart machine, the CPU usage is still 0. I'm not actually running anything on it. So just to stress the point, the load averages can be quite confusing if you don't understand the scope that they apply to. Over time, we may improve this, so please check the man page for, say, Uptime, or you may comment if we make this zone aware. And we're also developing something called Cloud Analytics, which will allow you to see the CPU usage in much finer detail across your smart machines, and also to look at the metrics such as dispatcher queue length by application. Thank you.